All right, this is Designing for Programmer Delight. I'm Richard Feldman. So I spent the early part of my career designing for non-programmers, that is, making software that was going to be used by people who were not programmers. I spent more and more time as my career went on, increasingly designing software for programmers to use, whether this is open source projects or just working in a larger group, and so I had a larger number of programmers interacting with my software. And I've definitely found that there's some sort of Venn diagram overlap between the two. So both of them involve understanding the goals of the people using the software, also understanding the needs of the people using the software, and those sometimes can be in tension, and also just understanding the preferences of the people using the software. One of the things I'm always saying is that programmers have preferences, and it's okay to understand that sometimes a design that works perfectly great for some people, just other people might not like it, and that's okay. But today I want to focus on just designing for programmers and sort of narrow in on 5 different aspects of designing for programmers. One is the usefulness of a piece of software. So can it address my use cases, the particular use cases that I as a programmer have? Another is the convenience of the software. So how convenient to use do I find it? How fast does it run? So the performance. Error proneness, in other words, like how often does using it lead to bugs, and then upgradability, like what's the upgrade story like? What's the experience of upgrading the software over time, and how often will upgrades break my code? And I'm going to look at these different aspects through the lens of delight. So delight is an emotional reaction that we have to a design. It's individual to the person. So some people might find one thing delightful, and a totally different group of people might find the same thing not delightful at all. And also emotions about a design can change over time. Something that we might find joyful or delightful or really pleasant to use early on can maybe end up leading us to feel regret. I've certainly found that in my career plenty of times about the same piece of software. So to really narrow this down, what I'm sort of aiming for when I'm thinking about designing for programmer delight is asking the question, how do we design our project so that programmers feel delight when using it, that emotional reaction, in both the short term and also in the long term? And so for the purposes of this talk, I'm going to sort of walk through an example of this, which is dictionaries in the standard library of the Rock programming language. So for those of you who are not familiar with Rock, this is a language I've been working on for several years. And dictionaries, I think, are a pretty good example because it's something that everybody's familiar with. So Rock has a sound static type system with 100% type inference. It compiles to machine code or to WebAssembly. Performance is definitely a high priority for Rock. Its goal is to sort of approach the performance of systems level languages like Rust or C++, although it does have automatic memory management. So it's never going to get quite as fast as those languages, but the goal is to be approaching that level of speed, which is especially unusual because of the last aspect of Rock, which is that it's a pure functional programming language. So most functional programming languages, and especially pure functional programming languages, are not this performance oriented. So we have sort of an unusual set of constraints here, but they're applied to a familiar problem, which is, standard library, dictionaries. A lot of different programming languages have dictionaries in their standard libraries, but just to be sort of clear on what I mean when I say dictionary, let me just give a little definition here. So what I'm talking about here is a key value collection where the keys are unique and they have some definition of fast lookups. And that, that's all relative, of course, to the programming language, but, they're sort of intended to have a lot of lookups, and so you want lookups to be pretty fast, ideally. For a little bit of context, Rock already has a feature called records, which are sort of fixed size structures, more like C structs, if you're familiar with those. So dictionaries are definitely slower than records, but they can be variable size. So when I say it's a key value collection, I mean not a fixed size collection. I mean one where you can do insertions and removals on the fly. Okay, so the design question we have here that we're going to try to analyze from the perspective of how to maximize delight is, what dictionary implementations, if any, should Rock's standard library ship with? Now, different languages do this in different ways, and I think one of the most important first things that you can do whenever you're looking at a new design question like this is to look at what are some of the existing designs for similar problems. Now, hopefully you're doing something novel here, and there isn't just an obvious answer because somebody's already done exactly this thing. They had exactly the same design constraints, exactly the same needs and goals, but usually you can find some similarities, sort of some prior art of like people doing similar things. So in our case, of course, with dictionaries and programming languages, that's why I picked the topic. There's plenty of prior art. C, for example, decides that it should have 0 dictionaries in the standard library. It's just not a data structure that ships with the C standard library. Ruby has exactly 1. It's a hash map. Elm has a persistent ordered map, so also only 1, but it's a different data structure. It's not a hash map, it's an ordered map. And then Java has, actually I think it's 7 different dictionaries, so like hash map and tree map and all these different varieties of ways to do dictionaries. So definitely a variety of different design space. Now, Rock is a direct descendant of Elm, so sort of the obvious answer would be let's use a persistent ordered map. But there are some differences between Rock and Elm, one of which is particularly relevant here, which is opportunistic mutation. So this is something that is different between Rock and basically most other functional programming languages like Elm, Haskell, Clojure. I only know of like one research language that also does this. And basically the optimization is this. We do in-place mutations when it's unobservable. In other words, we'll have an API that looks like it's sort of immutable and sort of it is semantically immutable, but we will detect when, you know what, nobody else is referencing this data structure, we're just going to go ahead and mutate in place. And this has a big impact on what sort of makes sense in terms of design of standard library features, especially around data structures like dictionaries. So, in particular, this means that non-persistent data structures are actually quite appealing, even though we're doing semantically immutable things. So Elm and Clojure and Haskell, they'll all use persistent data structures for their standard library stuff. But in Rock, we actually don't want to do that. We sort of would rather not if we can avoid it because it can be faster thanks to opportunistic mutation optimizations. So let's look at some of the trade-offs in these existing approaches that we've looked at in some of these different languages. So one approach is you can do a key value array. This is something where you just essentially don't bother doing hashing or any kind of sorting with trees or anything like that. You just have a flat array of key value pairs. Now, one nice thing about this is that it preserves insertion order, but it does have a downside of making retrievals pretty slow because you have to walk through the entire array. Ordered maps, like what Elm uses, these can be quite nice for sorting or unioning. So if you already want to end up traversing this thing in sorting order, the fact that it's already sort of sorted everything ahead of time can be pretty convenient. It means that you don't have to like sort it after the fact. If you want a sorted traversal, it's already sorted. Also, if you're doing things like unioning or intersections, sort of like set theoretic operations, ordered maps can be faster at that. Unordered hash maps will typically be the fastest of these in terms of like individual lookups and stuff like that. Now, if you do have too many hash collisions, that might not be true. In fact, they can actually be the worst if you have too many hash collisions. But barring that one use case, generally speaking, unordered hash maps will typically be the fastest in terms of like insertions, and they'll be the fastest at traversals aside from key value arrays, which are pretty hard to beat when it comes to just traversing the entire thing because it's just an array. Finally, key value arrays, worth noting that although they are typically the slowest when it comes to lookups, if you've got like string keys, for example, they can be pretty slow, but they can also be very, very fast if it turns out that your use case is something where you're just inserting them and then maybe just traversing them or something along those lines. And also especially if the keys are pretty short. So when it comes to asymptotic performance specifically, that is to say, like as the collection grows, what is the sort of slope of the performance increase or decrease? And generally it's going to be a decrease. So the best performance that you can generally get out of dictionaries is sort of special case things. Like you've got a dictionary that's really optimized for one use case. Classic example of this is you might say, we happen to have the invariant that all of the keys in this dictionary are monotonically increasing integers. At which point you can say, oh, well, this is perfect. I can just use a flat array to sort of map the values of this, and then the keys can just be indices into that. And so now lookups are just as fast as they possibly could be. That's pretty great, but it's probably not something that we can get away with in terms of like making the dictionary in our standard library do that, because one of the needs we have for a dictionary in a standard library is we want it to cover a wide variety of use cases. That's kind of the point of the standard library. If somebody has a special case thing, they're probably going to be reaching for something outside the standard library anyway. Asymptotic performance of hash maps is not as good as these sort of special case niche data structures, but generally, again, pretty good, especially when it comes to lookups. You can get constant time asymptotics. So basically, again, as long as you don't run into too many hash collisions, you can basically just say like the amount of time is not really going to vary based on the size of the hash map. It's always going to be about the same amount of time to do an individual lookup. Search tree is logarithmic, so the number of levels into the tree you have to descend should be bounded, so it shouldn't get too bad as the size of the tree increases. So you should have sort of one more hop to go every time the tree doubles in size, like doubles in terms of number of elements it's storing. So that's not as good as the hash map, but it's still better than the key value array where basically it's linear. Every single time you add one more element to the array, that's potentially, in the worst case, one more element that you have to traverse in order to answer a question like, I want to do a lookup into this thing, or even just detect if there's a value present in it. Now, again, like special cases requires, these very niche requirements like having consecutive integer keys. With the hash map, you do have to have the restriction that all of the keys have to support both equality as well as hashability. So you need to be able to say, for all the keys in this hash map, I need to be able to compare them for equality, and also I need to be able to hash them. In the case of a search tree, you have a similar restriction, except you don't need to be able to hash them, but you do need to be able to order them. So you need to be able to say this one is less than or greater than or equal to this other one. And then with the key value array, you have the least restriction because you're just comparing everything. So all you have to do is have equality. So in terms of like restrictions on them, key value array sort of has the worst asymptotic performance, but the most lenient restrictions on your key space. The special case ones have the most stringent ones. So to me, the sweet spot for a dictionary in a standard library is probably somewhere in the middle with like the hash map or search tree. Another consideration here is the traversal order. So in the case of special case, can't really say much about the traversal order. In the case of a hash map, generally speaking, by default, you have unordered hash maps where traversal is unordered. That is to say, it's not defined. Like the traversal is just going to be kind of unpredictable unless you know exactly what the hashing function is, in which case maybe you can figure out what it's going to be, but you're supposed to not rely on it. With the search tree, it's very predictable. It's always going to follow sorted order, and the key value array is always going to use insertion order, so whatever order they were inserted into the array. Of these, I would say that key value arrays insertion order is the most useful because the hash maps unordered search tree is useless. I mean, it's just by definition. In fact, it's saying like, hey, don't rely on this traversal order. Special case, again, it kind of varies based on what you're doing, so can't really get much out of that. But if you have insertion order, you can take something that's been sorted in insertion order and then sort it. In fact, you can sort any of these after the fact by any sorting mechanism you want to. But the reverse is not true. You can't go from something that has been storing it in a sorted order, like a search tree, and then go back and say, you know what, I would actually like to, I changed my mind, I want to get insertion order out of this. You can't do that. You have to have been recording insertion order all along if you want to, but if you were recording insertion order, you can always get it to be sorted later. So although that one's the most useful, again, I think the performance downside there is too severe, and I would kind of lean on, I think really in my mind, it's kind of down to hash map or search tree as sort of our dictionary of choice. Okay, so let's between these two, we know an upside is that hash map is asymptotically faster, but let's talk about what are the relevant downsides of choosing a hash map over a search tree, because it's not just about that performance consideration. There's other considerations to be had here. So one that we talked about is that search trees have, preserve sorting order. I don't personally consider that to be that big of an upside for something like a dictionary in a standard library because, again, we're trying to think about a wide variety of use cases here. How many use cases out of all the use cases that people use dictionaries for, is it the case that you really want sorted keys? I don't think that big of a deal. And again, there's like the set theoretic functions that I mentioned earlier, but also I don't think that's that big of a deal in terms of like the wide use case space that people have for dictionaries and standard libraries. So those are relevant downsides, but they're not that big. Upgrade story, I think, is a much bigger downside. So the upgrade story, if you're going to upgrade your sort of data structure's memory layout, that can be a non-breaking change for a hash map. And if you're upgrading a search tree sorting function in a tree layout, that's also going to be a non-breaking change. But if you have an unordered hash map and you change the hashing function, that is almost always going to be a breaking change. Like you change the hashing function, maybe it runs faster now, but if you were accidentally relying on traversal order, that's potentially going to break. Like your code might just have bugs in it now as a result of changing your hashing function. This definitely happens all the time in the real world. And unfortunately, accidentally relying on hashing ordering is like pretty common. Now there's a school of thought here that says, well, just don't rely on hash ordering and then you'll be fine. And that's sort of your fault if you relied on it and you weren't supposed to. Buyer beware. There's this famous law called Hiram's law. With a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. And I think this is a good example of this. Like, even if you say don't rely on ordering, you know that some people will do it even if you tell them not to. And you could say, again, buyer beware, this is your fault. You're the person who should feel bad if you're relying on this ordering and then your code breaks after we upgrade the hashing function in the standard library. But I'm sort of like reminded of this sort of comparison here, where like let's imagine there's a field and then there's a hole that's been dug in it, and you put a sign over it that says, "Hey, danger, open pit! Like this is a pitfall. Don't fall into it. There's a pit here." This is the responsible thing to do, but the delightful thing to do is just to not have a pit in the field. I mean, surely we can agree on both of these things. Like, yes, if there's a very good reason that the pit needs to be there, then it's better to put a sign over it than not. But it's much preferable if you just don't have a pit in the field and then there's just no need for the sign. There's just, hey, you can just walk on this and it's fine now. So let's see if we can find a way to get the more delightful design where we are not running afoul of Hiram's law, and we know that we can upgrade our data structures performance in the future with like better hash functions as they're coming out, because new faster ones are coming out all the time, and also new hardware improvements are coming out, meaning that you're allowed to make new hash functions using things like SIMD that weren't available before. Can we do that while still giving a delightful experience of just having all of your code continue to work? Well, here are some ways that I don't think are going to work to prevent bugs from hash function upgrade. One is don't have a dictionary in the standard library at all. Well, that's the whole point of what we're trying to do here is trying to find a way to put a dictionary in the standard library. You could also say, hey, just never upgrade the hash function. That'll do it. Again, doesn't make sense. Like if new hashing functions are going to come out, we're going to want to upgrade to them to make things run faster. You could say don't support traversal or require sorting first, like before people can do traversals. But again, I don't think that's particularly realistic. It's important to be able to traverse your hash maps. That's like, one of the basic use cases that you're going to have if you want to have a dictionary in the standard library is people are going to want to traverse it. And then finally, you could say we'll just randomize hashing order in order to sort of surface reliance on hash order. You can find out ahead of time that you were accidentally relying on it because your code's going to break pretty quickly in your tests if every single time we do the hashing, we randomize the order for you. This might seem like a reasonable design. As I understand it, I believe Go does this, but I have a couple of problems with it. One is that it means that if you're unlucky and your code path that is relying on hash ordering happens to not get run in your tests or not get run under the circumstances which would cause it to break, then you're still kind of in trouble. But more importantly, this is a pure functional programming language. The definition of a pure function is every time you call that function with the same arguments, you are expected to get the same return value with no side effects. This breaks that. This breaks the property known as referential transparency, where you can rely on being able to call any function in the programming language with the same arguments and get the same return value out. Now you could say, and I've heard this argument made, and I think it's a reasonable argument, that referential transparency is only important within the scope of a single running program. So if, for example, you said, we're going to randomize this, but we're only going to randomize it for the duration of your program. For some reasons I won't get into that are Rock specific, that's not ideal based on how Rock is intended to be used in practice. But more to the point, there are some reasons that we would want to rely on that property across different invocations of the program. For example, one of the features that would be really valuable for us to be able to have, and something that we're actively planning on developing, is the ability to selectively rerun tests based on our knowledge at compile time that some tests 100% guaranteed will give the same answer as last time and therefore don't need to be run. This is potentially a very big cost savings in terms of like how much time you might spend running your test suite if we're able to say, hey, you know what? None of these code paths changed since the last time you ran them. We have them cached on disk, and we can tell that these tests only depend on code that didn't change. Therefore, there is no chance that these tests will give the wrong answer. Now, that's perfectly fine as long as we happen to know that every time you run the program, you're going to get the same answer. But imagine if we introduce that feature and then suddenly some of your code started actually breaking when you made changes because it turned out that you got lucky on a previous test run and then you got bad luck on a subsequent test run with the randomly generated hashing function. So this is a very big invariant to give up for the sake of solving this problem, and it's one that I'm not willing to give up. So we've ruled out all of these ways to prevent bugs from hash function upgrade. So what do we do? Well, fortunately, around this time, or in the course of doing this design process, ended up discovering this data structure called index map. Without going into too much detail, here's a brief primer on how it works. Basically, you start with a key value array. So that data structure we've been talking about earlier was just a plain old array of keys and values, and you can just index into them by index into there. But we add a separate hash map on top of that, and this hash map maps indices into that array. So you start with a key, and you give the key to that hash map, and what it gives you back is an index into the key value array. Now we can say, okay, well, I've got a key. So if I take the hash of that key and get that out of the hash map, now I have an index. And now I can just take the index of that array, and that gives me back my final value. So there's one extra step to a lookup or to an insertion, but this has some pretty cool properties. So one is, from a performance perspective, lookups take, okay, one extra memory access, granted, but you have to keep in mind that if you're doing a whole bunch of lookups in a row, there's a pretty good chance that the subsequent lookups are going to be in cache and are not actually going to be particularly expensive because they're coming out of the same array and out of the same hash map. Traversal is maximally fast. In fact, this is even faster if you're traversing this thing than it is to traverse an ordinary hash map, an unordered hash map, because it is literally as fast as it possibly can be. All of your key value pairs are right next to each other in memory. So you're just going to be walking straight through the array and saying, here's the next one, here's the next one. It actually is not possible to make a data structure, as far as I'm aware, that's faster than that for the traversal use case. So yes, lookups do take an extra memory access, but depending on the pattern, that may not be a big deal, depending on what ends up being in cache if you're doing a bunch of lookups in a row. And traversal can be faster. So depending on how frequently you're doing lookups and traversals, like the access patterns, it's actually conceivably possible that index map could actually outperform unordered map, again, depending on the particulars of the use case that you're using. This has been benchmarked in the Rust compiler. There was a branch where somebody replaced the unordered hash map in the Rust compiler, which does a ton of hashing. And the performance is basically equivalent, or like overall, all things considered, to the unordered hash map. So the author of that pull request was actually hoping that it would end up being faster based on their usage patterns in the compiler, and that they would end up switching to index map. But it turned out it was about the same, so they decided to not bother switching in order to not bring on the dependency. But to me, that's a really important thing to know about, because this is not just a theoretical benchmark. This is actually like a very large and like real-world battle-tested code base where they actually demonstrated real-world performance of this being about the same. So to me, this makes index map a very real contender for what we should use as our standard dictionary. So now when we need to sort of like revise our consideration of like what are the asymptotic performance characteristics of these different things. So now we have sort of hash map or index map tied in second place. I'm going to treat them as essentially tied in terms of overall performance, since it is kind of use case dependent, but very, very similar in practice, it seems to be. And then both of those are faster than search tree. But there was another wrinkle here, which was discovering hash flooding attacks. So a hash flooding attack is a way to amplify a denial of service attack. And basically, you induce collisions to make insertions be worst case. So you fire a bunch of JSON, for example, which is potentially some of that's going to get decoded into a dictionary or a hash map, or a bunch of HTTP headers that are designed to be basically specially crafted in order to have collisions on your particular hash function. This is something that only hash maps are vulnerable to. So like ordered maps, not vulnerable to this. But this relates to the consideration we were making in terms of randomized hash keys, because the most common mitigation that programming language, standard library, dictionaries that are hash maps use to mitigate this is to randomize their hash function with a randomized seed, so that the attacker can't predict what payload they need to craft in order to make the attack work and to make the collisions happen. But that's not the only way to mitigate hash floodings. So one other option is you can say, I'm going to mitigate it in the web server, not in the standard library. This is a totally valid approach to take. Honestly, among all programming languages, this has been really uncommon. Most modern programming languages have said, you know what, it's our responsibility to mitigate hash flooding and not the web servers. So we're going to make changes to the standard library. And so a lot of really common popular programming languages actually do have randomized hashing functions, either by default or as the only way to do it, because of hash flooding attacks specifically. So if you did want to mitigate it in the web server, this would involve things like, for example, changing how you parse HTTP headers so that maybe they don't go to a dictionary. Maybe you have to specify a sort of like parsing feature that like enumerates, here are the specific ones that I care about, and we're not going to bother putting the others into a dictionary because they might result in hash flooding. Trickier with JSON. So with JSON, you might say maybe we're going to decode JSON not into a standard library dictionary that's a hash map, but rather we're going to decode it into an ordered map that doesn't have this problem because it doesn't have a hash function to cause collisions on. So like I said, that's an option, but it's not a popular one, so we can keep it in mind. Another is, again, just say, hey, maybe this is an argument that says we shouldn't actually use hash maps in the standard library after all. Maybe we should go with the ordered map approach because it doesn't have this problem. Also, you could say we'll do what basically most languages do, which is to use a flood-resistant hashing function. So SIP hash is like the most popular one for this. It was designed for that. There is a pretty significant performance downside to using this, not just because of the randomness, but also because just as a hashing algorithm, SIP hash is just not one of the fastest ones out there. There's way faster hashing algorithms you can use if you're willing to not deal with hash flooding or to deal with it in a different way. For example, using a flood-resistant collision resolution strategy. So the hash flooding attack sort of relies on the assumption that when you have a bunch of hash collisions, you're sort of going to fall back on the same type of linear performance you would see in like that key value array, where you're just having to check everything one after another, and you're essentially not dealing with the hash map's performance in terms of lookups anymore. Java 8 did this strategy. They basically did not change the hashing function. They instead changed their collision resolution strategy to make it so that after a certain number, I think it's 4 collisions, then it falls back on storing subsequent collisions in an ordered map so that you get that sort of logarithmic lookup time instead of continuing having it be linear. So all of these different strategies, have pros and cons, but to me, the flood-resistant collision resolution strategy really kind of seems like the best approach if we can. It means we don't have to deal with any of this randomness stuff, which messes with our referential transparency. It means we don't have to sort of push the responsibility onto the web server, and maybe that has weird incentives for like the JSON parsing ecosystem and whether that uses the standard library dictionary. And it means that we still get to use hash maps in our standard library and get all the performance benefits from that in every other scenario other than things that are actually vulnerable to hash flooding attacks, which is really only web servers. Okay, so flood-resistant collision resolution. What's up with that? So basically, to summarize the sort of general approach, it's like use a search tree which has logarithmic time and requires not just equals and hash on the keys, but also this like ORD constraint, so you know how to order the keys. You can also just use another hash map with a different hash function. I have seen arguments that this would work, but I've also seen like further analyses that seem to suggest that this actually would not be enough in practice, or that like this could be defeated by carefully enough selected attacks. I don't know if this has been demonstrated in practice, but it is certainly, to me, more concerning than the approach of falling back on a search tree. You can also use a seeded hash map, so like something like what SIP hash does, but again, not really interested in getting into randomness. And really, I mean, to me, index map is interesting in this area because it means that this collision map can potentially be unordered. So index map had this property of insertion order is maintained, but if we've got that for our keys, and sort of like the sort of primary data structure, if we happen to have a separate collision map that is unordered or ordered by sorting, like because it's a search tree, that's totally fine. That's something that doesn't have to be exposed to the end user or affect them at all, because whenever they do any traversals, it's only going to be traversing on sort of this main key value array. It's never going to sort of have to go into this sort of collision space at all. So that to me is a big benefit of this index map design, is that it means we don't necessarily have to pick one of these. It's something that we can sort of seamlessly upgrade to in the future without having to have that design nailed down on day one. So yeah, there's multiple feasible solutions here. Seems solvable in multiple different ways now that we've sort of explored this possibility space. Each specific design is going to have its own trade-offs. And really to compare these, I think we would need to at least implement one of them in order to sort of see how it goes. So fortunately, like I said, this design doesn't have to be set in stone. It's just like, the first one we're going to try building is sort of what we're trying to pick out here. Okay, so to summarize all that, index map upsides. Traversing in insertion order, which is, by the way, the most useful order, because as previously noted, if you're preserving insertion order, you can always sort after the fact, but you can't go the other way around. Like if you're sorting, then you cannot retrieve insertion order. You've just sort of lost that. Traversals are slightly faster than an unordered hash map. Not going to say it's night and day different, but it is the fastest way to traverse. Hash function upgrades are a non-breaking change because it preserves insertion order and because it always traverses an insertion order regardless of what the hash function is. And also we can now mitigate hash flooding with one of those different non-breaking changes, and it's going to preserve referential transparency no matter which sort of solution we decide to go with. Now, there are some index map downsides. Having said that, we did note that lookups are going to be slightly slower than the unordered hash map. And also, one that I didn't talk about is that there are two ways to do removals in index map. One is quite slow, which is to say, let's say you remove something from the index of the key value array, and you just shift everything over in order to preserve insertion order. That's pretty slow because you have to shift every element after that insertion removal point over. That can take a while, but there's a much faster strategy, which is basically you have your key value array. You say you want to remove something in the middle, you basically swap it with the last element in the key value array. So swap that thing in there. Now you still have a contiguous array of key value things, but the order has changed. It's no longer got that original insertion order ordering. So this is a downside, is that if you're using an unordered hash map, nobody really expects removals to, nobody cares if removals do or don't change order because they're already not relying on ordering. In an ordered map, removals don't affect ordering at all. It just maintains the sort ordering. Although there is a performance downside there. Sometimes you might have to rebalance the tree periodically. But in the case of index map, if you want the fast removals, you can have very, very fast, just swap these two things and you're done. Very fast, but does change the ordering. Slower removals with the remove shift. You can offer both of those, of course. They don't change the ordering, but they are a lot slower. So this is a downside that doesn't exist in quite the same form in either the ordered map or the hash map that's unordered. Okay, so we sort of really fallen down the rabbit hole here, right? We just started with this question of hey, what dictionary should we use? Should we have one dictionary or multiple dictionaries? And now we're all the way down into hash flooding and all these different data structures. And I was like, okay, so this is normal. This is okay. This to me is part of what a healthy design process looks like. Is we do go down these rabbit holes and we do explore things and go really in depth on lots of different things. But then at some point, we sort of have to say, okay, let's just take stock and try to summarize, where did we end up? And what conclusions can we draw from this? And does this give us a path forward? So we talked about these existing designs for similar problems. C says just don't have a dictionary as standard library. Ruby and Elm say let's have one. Java says let's have more than one. To me, I always like to think, if we can just have one nice, obvious default, that's a really nice quality to have in a standard library data structure. And to be honest, I think we found one that's a good contender to say yeah, we can have just one dictionary data structure in the standard library that is going to address enough of a wide variety of use cases that it's going to be a good default choice for basically 90+% of the time for the different things that I think people will use Rock for. So to this question of should we go with a hash map? We said it's got great asymptotic performance, but then again, future hash upgrades could be breaking changes if it's unordered. But then again, index map can address that with some trade-offs. But then also SIP hash breaks referential transparency, but we can fix hash flooding in the data structure later without having it be a breaking change thanks to index map. So it's okay, well, if we sort of look at how these things sort of balance out, again, there are trade-offs and nuances to all of these things, but it's kind of well, okay, future hash upgrades could be breaking, but they aren't if we use index map. And yes, SIP hash as a hashing function would break referential transparency, but we can fix hash flooding with various data structure mitigations, like doing what Java 8 did, and we can do that later as a non-breaking change if we're using index map, because then it means that whatever fallback strategy we use for resolving collisions can be completely unordered or ordered according to sort order, anything we want, and that will not affect anyone's traversals because they'll continue to be ordered based on insertion order. So we're really kind of down to should we go with a hash map for this? Well, it's got great asymptotic performance, and all of the other concerns have now been addressed in various ways. So yeah, I think we should. So the front runner design, obviously, for this is going to be based on index map. So this is a hash map that is preserving insertion order. So that is the most useful thing. It's useful in the widest variety of use cases. If you have a design, and there are some designs, some use cases where maintaining insertion order can be quite useful. I've talked to different people who are like, yes, this is definitely something I want. It's not something I always need, but sometimes I have run into situations where that's very helpful, and I would like my standard library dictionary to have that. That would be great. It's still referentially transparent. It uses the fastest hash function that's available, and that includes future hash functions that don't exist today. Like when they come out, we can upgrade to them as a non-breaking change. And we're going to be able to mitigate hash flooding attacks, so it would seem, in the data structure. Granted, mitigating hash flooding attacks in the data structure for the fastest category of hash maps, I don't know of anyone who has done that yet. So this is sort of like an open implementation problem. If you're interested in working on that, please get a hold of me, because this is something that we would very much like to do and to implement. And I think it's like a pretty cool problem if you're interested in like really low level like hash map implementations. This is a useful use case for doing that. Okay, so we've considered a lot of trade-offs here. So sort of zooming out, we talked at the beginning about usefulness. I think insertion order does cover the most use cases. So this is sort of like the maximally useful ordering to do for your map. Convenience, we talked about how remove runs fast but changes order. So I would say this is sort of the one thing that I would say is inconvenient about this design is that the remove function changes the order of changes your ordering from insertion order into something else, and that is a downside. But I think taking this into account of all the other trade-offs, I think that's an acceptable one. But it is a downside in terms of convenience. In terms of performance, this is basically going to be like typically I think tied for fastest, and it's capable of mitigating hash flooding, which is of course a performance concern. Tied for fastest meaning that unordered hash maps are also about equally fast, but index map is in the typical case, it seems like it's going to be about as fast. Although, that may vary depending on how many traversals versus lookups you're doing. Error proneness, again, I think remove is kind of the only real concern that I have here. And I do think that any bugs that would come up related to remove changing the order would likely come up and be pretty obvious right away. Like if remove changing the order ends up breaking something, that's probably going to be because that you were actually relying on the insertion order, and you're probably going to see right away, oh, after I called remove, this was no longer in the order that I expected. Could be wrong about that, but my guess is that any bugs that you would see from remove would not be like all that hard to track down. Only one way to find out though, which is to implement it and try it out. And finally, upgradability. It seems like with this design, we get upgrades that are pretty backwards compatible. So I want to note though that again, these are all trade-offs. Like, this is not a slam dunk. It's not like this is the obvious design. Of course, when we set out at the outset, this is like the obvious choice that we should do here. There's a lot of trade-offs here, and this is not perfect. It's not flawless. It's not without its downsides. But it seems all things considered for the particular use case of, Rock as a programming language, what it sort of wants, what its goals are, this is going to be the most delightful design, I think, that we can come up with. Okay. I want to quickly note, there are some risks to doing a sort of like quick and dirty design process or like, sort of rushing it, like compared to, all of the amount of like time that we spent. And, of course, I'm condensing down a lot of conversations and design work that we did, into like these sort of bullet points. But you can do it a lot quicker. But I think there are some sort of risks that should go explicitly spoken and not go unspoken about doing a quicker design process. Like in terms of usefulness, like what if it turns out that you just can't cover important use cases? Classic example of this in this case would be insertion ordering. What if it turned out that a lot of people had that as a really important use case, and we'd gone with an unordered hash map, and they said, oh, this standard library data structure is now just not usable in my use case. It would have been fine to make that choice consciously and say, okay, yes, but we think that's a niche use case, and like we're gonna choose not to cover that, versus sort of going in without being aware of that and thinking, oh well, we just are surprised by it later on. I don't know, hopefully it turned out not to be important. So just doing that diligence to figure out like what are the useful set of use cases that you want to cover. If you don't do that, there's a risk that you're just going to be surprised by these important use cases coming up. Convenience. What if it turns out that, we had just sort of done this quick and dirty design, and we found that like, okay, in basic use cases, this works fine. But then as you get into more advanced use cases, it turns out that this design is actually pretty painful. That's always an unpleasant thing to discover too late after the fact. Performance. It's pretty common for people to sort of gloss over performance and to start off with something that's feels like it's going to be fast enough, but in practice, it just is not. It's just too slow. And then, of course, you have the really scary question is, can it be fixed? And can it be fixed without breaking everyone's code and having to change to like some completely different strategy that maybe has different usefulness, convenience, etc. Guarantees? I think it's really, really risky not to design for performance, at least in the large from the get-go, and to have a plan for how this is going to be fast. Not saying you need to like bust out the flame graphs, on day one, but there needs to be a lot of thought put into like how is this going to be fast if you actually want it to be fast, and very early on in the process. Error proneness. What if the design, is very convenient, it's very fast, it's very useful, and it's full of foot guns. I've definitely used software like this before, and rushing through the design process and not discovering those foot guns, not even thinking about, like asking the question of, like in our case, what if remove turns out to be a foot gun? I don't think it will be, but like, not thinking about that type of thing risks just finding out the hard way. And finally, upgradability. This is another one that's really easy to gloss over, and again, it doesn't bite you up front, but this is exactly the type of thing where designs can feel delightful in the short term, and then over the long term, oof, they just really stop being delightful because you're feeling changes from I used to like that thing, and I no longer do, because every time I upgrade it, it's really painful, or there was a really really nasty upgrade thing that caused all these bugs, and thinking about upgradability, definitely a risky thing to ignore early on in the design process. Finally, I'd like to sort of leave with this one of my favorite quotes, and I don't know who said this, but I've heard it a couple times and phrased a few different ways over the years. But a month of implementation can save a week of design. Really true. I think we live in a culture where like there's a lot of celebration of like move fast, iterate quickly, and definitely iteration is important and moving fast is valuable. But design is also valuable, and sometimes even in like the medium term, let alone the long term, spending some more time on design can be absolutely the fastest way to move. Okay, so summarize all the things that we talked about very quickly. Started off talking about how designing for programmers and designing for non-programmers has some overlap, but also, this talk is mainly focused on the sort of designing for programmers aspect. Talked about how it's important to start by looking at existing designs for similar problems. In the case of standard library of rock and dictionaries in there, obvious choice would be do what Elm does. But actually, after exploring the problem space and thinking more about our specific needs as a language, it ended up turning out that we wanted to do something different than what Elm does. And that totally makes sense. And we really would not have known that unless we'd actually sort of gone through this whole process. Opportunistic mutation is sort of like the key that led to all these explorations. That's like the optimization that Rock does that these other languages don't do, which ended up leading us to index map of all things. For languages that don't have referential transparency, they're not pure functional languages. Unordered hash map probably makes a lot of sense, or a lot more sense. But in our case, even though we know that insertion order is like potentially going to be a little bit slower, this probably makes the most sense. It means we get sort of the widest range of usability because we get to maintain insertion order. We know that traversals will be slightly faster, but lookups will be slightly slower. Upgrades can be non-breaking changes to a hashing function, and we have a strategy for how we're going to mitigate hash flooding, even though we haven't implemented it yet. And finally, I want to leave you with this image, which again I just love. If you have the option of taking something and you got a big hole in your field and you're thinking about just doing the responsible thing and labeling it, try, if you can, just thinking of a way that you can instead make it so that there is no hole at all for people to fall into, because that, at the end of the day, I think is the way that you get the most delightful design. Thanks very much.